Hello, Titans. I want to make a video here to deal with the concept of specific heat. Specific heat. Um, to do so, and don't worry about that word for now, but I'm going to start out with this scenario here. I have a beaker of boiling water. It has 500 grams of steel in it, and it is 500 grams of water that's boiling, or very close to that. A little bit maybe is boiled off, but it's close. Down here, I have two beakers, each containing 500 mils, 500 grams of water at 20 degrees Celsius. They're both at the same temperature. They've been sitting here on the counter for a couple hours. So these are both 20 degrees room temperature. But again, in the beaker, I have boiling water and steel in it. Both are at the same temperature, which I hope we recognize as 100 degrees Celsius boiling. What I'm going to do is I'm going to take the steel out of one of those and put it in this beaker, or steel out of one of these. Take the steel out of the boiling container, put it in here. I'm going to take the water out of this container, both 500 grams. The steel and the water are both 500 grams. I'll pour the water in here, steel in here. My question is, what will happen to the temperature of these two beakers? They are both at 20 degrees Celsius. They both have the same amount of water, 500 grams each. This one will have 500 grams of water added to it at 100 degrees. This one will have 500 grams of steel at 100 degrees added to it. I want to know which one will change temperature more, or will it be the same? Will they both end up presumably higher than 20 degrees because they're getting hot stuff poured into them or placed into them? Will this warm up more, or will this warm up more? This one has water added to it, 500 grams. This has steel added to it, 500 grams. Think about that for a moment. If you need to pause me, that's cool, and give it some thought, but I'm going to do it right here. So I'm going to drop my 500 grams of steel. I'm not going to drop it. I will set it because I don't want to break it. 500 grams in there. And now I will take 500 grams of water into the other container. All right. I'm going to turn off my hot plate. All right. So these are both, giving up their heat to the original water that was in there. I'm going to record the temperature of each. This one will mix very quickly, so I'll get its temperature. It was 20 degrees Celsius. It is now, thermometer's still going up. It says 50, 54, 53, I guess. So as I stir this, the hot and the cold are mixing. It's 54 degrees, 54 and a half. Feels like we're about there. 54 and a half degrees. Okay, that's when water was added. Now this one, excuse me, I added steel, the same amount, 500 grams to the steel, or to the water rather. Taking a little while for the steel, and it's a little harder to mix up. Steel, as it turns out, is going to give off its heat pretty quickly to the water. And my question is, what's going to happen to the temperature here? We said originally it was 20 degrees. The other beaker went up to 55, 54 and a half maybe. This one is reading, it started at 20. It's now reading 27, maybe 27.5. That's generous. And it appears to be finalized. It's not changing anymore. It's barely above 27, maybe 27.5. So this one went from 20 degrees to 55. This one went from 20 degrees to 27, maybe 0.5. What's different? Well, the same amount of water added to this beaker, same amount in terms of grams, same mass of water added to the beaker, had a lot more effect on the container. This feels very warm to the touch. This doesn't feel like much. It's not above room temperature very much. How does that happen? Something, I'm going to move my screen around here. Something is different between steel and water. That the water packs more of a punch, if you will. It has more of an effect on the thing we added it to. Water has a larger capacity to store heat, if you will. It stored more heat than the steel did, apparently, and gave up more of its heat to the steel container, or excuse me, to the other container of water, I should say. So the amount of heat present in a sample has something to do with what the sample is. Water is very different than steel, for example. We call that difference the specific heat. So the specific heat often that's called specific heat capacity. That's why we use the symbol C for specific heat. That's a lowercase c. So specific heat is a quality of water and steel that tells us how much, for a given amount of water, how much heat it can contain. Okay. Water apparently has a higher specific heat, quite a bit higher than steel does. In fact, there's a table in your text. I have it on my screen over here. We'll take a field trip to my screen here. So from my perspective, that video is backwards, but I think maybe yours is right. This is in our textbook though. And actually, if you know how to work the Google, you can ask the Google for a table of specific heats and you can find a whole bunch of things. You will find water at the bottom of the list. It says 4,186 joules per kilogram per Celsius degree. That's the units that we're generally going to use. Steel isn't on our list, but iron is. Iron is 448 calories per gram per Celsius, excuse me, joules per kilogram per Celsius degree. So water was 4,186. Iron is 448, almost 10 times less. If we look at the amount of temperature change, the iron sample went up from 20 to 27, so about 7 degrees. The water sample went up from 20 to 55, so went up by 35 degrees. 7 compared to 35, that's a 5 times difference. It should have been more like 10 times difference, but I think we weren't at all insulated here, so we probably lost a lot of heat along the way. But it's true that water has a much higher specific heat than iron. That is a big deal because once we know about specific heat, we can calculate how much heat is present in something. We do that with a pretty simple equation. Q is the heat present. Q, the amount of heat in a sample, depends on a few things. One piece is the specific heat. Another piece, and I don't think this will surprise you, the mass of the sample. That's why I set both of these as 500 grams, so that wouldn't be a factor in our experiment. But mass matters, specific heat matters. So when we're talking about how much heat is present, the mass matters, the specific heat matters. The other thing that determines how much heat it takes to heat something up is you want to know how much you're heating it by. How much heat does it take to warm up? How much heat does it take to warm up a sample of water by 20 degrees? Well, take your mass of your water, your specific heat of water, and your delta T, and you should be able to calculate how much heat it takes. So for example, if we do have, say we have a liter of water, that is 1,000 grams, and the specific heat of water is 4,186 joules per kilogram per Celsius degree, which reminds me, I probably shouldn't have called that grams. Can I change that to a kilogram? Instead of 1,000 grams, let's call it a kilogram. And what did I say? We were heating our sample up by 20 degrees. Celsius cancels, kilograms cancel. 4,186 times 20 will tell me how many joules of energy it took to heat up my water, my liter of water, by 20 degrees. I'll let you do the math. So what does that mean? I showed you the table. Maybe you might have been nice to have a screenshot of that table or to have a table handy in your notes. Water is huge compared to anything else on that list, which tells you water, when it's at a high temperature, it's containing a lot of heat. The downside is it takes a lot of heat to warm up that sample of water. What does that mean? It means a watch pot never boils. You can set a pot on the stove. It takes forever to warm up that water. The drop a pan on the stove, it warms up so fast because steel's got a very low specific heat. It's easy to heat up steel. Water, though, takes forever to warm up. The other side of that is water takes a long time to cool down. So if you have a hot container of water, it stays hot for a long, long time. It takes a lot to cool it down. In fact, for that reason, temperatures, any place near the coastline, temperatures tend to be fairly moderate. They don't warm up too much or cool down too much because the water acts like an energy storage tank. So if the temperature gets too high in the air, the water absorbs that heat and warms up the water a little bit. It's a huge tank of water, right? So the air never gets too hot. On the other hand, in the winter, the air gets really cold, but the water gives up its heat to the air and warms up the air. Because water has such a huge specific heat, it moderates the temperature. That's why if you go up north to Anchorage, for example, which is way up in Alaska, a long ways north, people swear it's going to be really cold there. It's not. In the wintertime, average temperatures in Papillion are colder than the average temperatures in Anchorage, right on the coast in Alaska. Now, you go inland in Alaska to Fairbanks, it's crazy cold. You're a long ways from the ocean, and it gets very cold there, way colder than here. So specific heat is a big deal. We can use specific heat to calculate energy. Remember, heat is a version of energy measured in joules. In fact, once we know joules, we can set up our law of conservation of energy, and we can say, well, if this is a certain number of joules, what if I set that equal to, I don't know, potential energy? Can we turn things that have potential energy into heat? We know we can. So I could say mgh equals mc delta T. I talked in class one time about Niagara Falls being warmer at the bottom than at the top. How could I calculate that? Piece of cake. mgh for the water at the top equals mc delta T, the energy changed into heat. You can calculate the delta T, how much it warms up. Easy problem. All right. So there's a quick synopsis of specific heat and how we can use that to calculate energies. And I'm gonna stop this video here. Next, I'm gonna make a video about how we can do basically the problem I just did here with my beaker, how we might calculate final temperatures. That's a different kind of problem, but that'll be our next video. So for now, I will say goodbye. Have a wonderful day. If I could find my cursor, it would be great. There we are. Goodbye, everybody.